session, we're going to have actually an announcement by Kunal Pawla.
So the Foundations of Responsible Computing Conference will be at Stanford, June 7th to 9th. Registration is open. Go to responsiblecomputing.org, register. There is a list of accepted papers there already, and the program should be there in the list. Yeah, it should be a great conference, and it's nearby, so hope you all make it.
Thank you, Kunal, for your service as a PC chair. Great, yeah, and I think it will be a great continuation of a lot of the topics we've been discussing this week. So hope to see many.
I have a quick question. How much does it cost to register for this conference?
Will be exactly $0.
Okay, exactly $0 for registration. Paid in full to OMAC.
We need to register. Free registration, but do register so we know how much.
What an incentive.
Sorry?
We want -$.
Exactly. And you get 50% off if you register by make it.
Okay, great. So thanks everyone for coming to the afternoon session, the final session for today. For our first talk of the session, we have Charlotte, who is a PhD student at Stanford, who's going to be telling us about the sample complexity of realizable multicalibration.
Okay, thank you everyone for joining me for my talk. And yeah, as Michael said, I'm going to be talking about the sample complexity of realizable multicalibration. And this is highlights from two recent works that I did with my amazing collaborators, Lunja Hu and Omer Reingold, who are both in the audience if you have questions. And my plan for the talk today is kind of two parts. So in the first part, I'm going to talk about this realizable multicalibration. And I'm going to tell you what I mean by that, how we start thinking about its sample complexity, the main result, and then a little bit of the techniques. And then in the second part, I want to go over briefly some additional results we got along the way to this main result. And this is in no way a comprehensive overview of what we have in these papers. There are a lot of additional results, but I think at least this one I want to highlight just as a direction for future work. So luckily, due to all the great talks that have gone before me in this workshop, I don't need to do that much to motivate multicalibration. But I do want to say that beyond its original proposed use as a multi-group fairness guarantee, we've seen all these very strong properties that it can give us, such as loss minimization, this robustness to distribution shifts, and more generally, we can think of it as this customizable notion of predictor quality, where by choosing our subgroup class, we can kind of define what sort of errors we care about and what sort of errors we don't. And so with this in mind, it becomes interesting to really understand how hard it is to learn a multi-calibrated predictor, and in particular, how many samples do we need? And so the setting that we usually think about is one where I get samples, IID from some unknown distribution, I input it to my learning algorithm, and then I want to output some C alpha multi-calibrated predictor. And I'm not going to belabor the definition of multi-calibration, but this is the type I'm using here. And it's calibrated with respect to this class C, which here is a binary class. Our results will extend to this more general real valued class as well. And the thing I want to highlight here is that we can assume anything about this distribution. So this algorithm is going to work no matter what nature really looks like. And we have nice algorithms to learn multi-calibrated predictors. The original HKRR algorithm tells us we can learn in something like log of the size of the set of subgroup samples. And of course, this is ignoring all sorts of error parameters and whatnot, just for simplicity. And so the question we're going to care about today is, what if I make some sort of distributional assumption? So maybe I know something about what my world actually looks like, or I have a constrained set of distributions that my data could be coming from. And then the question becomes, in this case, do I still need this something in terms of the size of C samples, or can I actually do better in certain situations? And so this is what I'm calling realizable multicalibration. And for those of you familiar with realizable pack learning, it should look very similar. And so my learning setup is going to look very similar, But I'm adding this distributional assumption here, that when I see my data, there exists some hypothesis from a constrained set of hypotheses, such that all of the labels of my data match the predictions of this hypothesis. And again, kind of as I said with respect to the C, I'm assuming that this hypothesis is binary coming from -1, 1, but our results extend to the more general case where these hypotheses are real valued, and that's just telling you the expected label. So are there any questions about this model that we're going to be working with, the realizable multi-calibration? So now that we have the model, we can talk about the goal, which, as I noted, is the sample complexity, or how many samples do I need to learn in this setting. And ideally, what I'd like is some notion of dimension parameterized by both my hypothesis class and my class of subgroups. And I want it to characterize the sample complexity. And so what I mean by that is I want it to be an upper bound. So I can give you an algorithm that needs roughly that many samples and can output a multi-calibrated predictor. But then it's also a lower bound. So for every class or set of classes, I can give you a worst case distribution where I actually need roughly that many samples to learn. And in the classic, pack learning single hypothesis class case, we have a very nice notion that gives us this. So VC theory or VC dimension, which some of you may be familiar with, but I'll quickly review, is this notion of the maximum size of some subset in my domain where I can choose any possible realization of labelings, and then I can find a hypothesis that matches those labelings. And I call that a shattered set. And so VC dimension tells me the size of the maximum shattered set. And you can think of this as a notion of expressiveness. So like, how many different types of worlds can my H really capture? And what's nice is that we know that the sample complexities of realizable and agnostic pack learning are both, VC in terms of the VC dimension of H. So already from this VC dimension notion, we can get a natural upper bound on how many samples we'll need to learn in this realizable setting. And it's also already an improvement from what we had before. So I claim we can get the minimum of the VC dimension of C and the VC dimension of H. So how do we get this? Well, on the one hand, we have this standard multi-calibration algorithm that can give us a multi-calibrated predictor with VC of C samples. I said log size of C before. You can massage it using standard arguments to get VC of C. And on the other hand, because multi-calibration, or the notion I'm using, is a relaxed version of standard accuracy, I can just straightforwardly learn H, give you a good H, and I've also satisfied this task. And so this means that I can really look at my two classes, decide which one is more simple, and just learn using that. And so I immediately get this bound, which when my H is very simple means I'm already getting an improvement over this more agnostic setting. But the question is whether this is the characterization that we want. Is this a lower bound as well? And maybe somewhat surprisingly, the answer is no. And so I'll give you an example on when this upper bound is not necessarily tight. So the example I want you to think about is I have a domain of data and I've split it up into two halves. And so right here, I have kind of two copies of the domain on the board, and I want to talk about what's happening in my class of hypotheses and what's happening in my C class. And so on the side with H, half of the domain is completely constant. Any hypothesis you look at is just going to have all ones. On the other half of the domain, however, H is extremely expressive. Let's say any possible labeling you can think of, I can find an H that matches this. So going back to the VC theory that we talked about before, this is going to be a very, very difficult class to learn. It's going to be VC dimension roughly the size of this right half of the domain. And so I'm going to need many, many samples to learn a good H. Now, on the other side, I have something similar going on for my class of subgroups, but things are flipped. And so on the side where H was very expressive, I actually have no subgroups that care about this half. So you can't find any individuals that are part of a subgroup. Whereas on the other side of the domain, where H was constant, now any particular, like any arbitrary subset you can think of, I can find a subgroup that exactly matches that subset. And so again, this is going to have large VC dimension. This is going to be very difficult to learn. And so using that minimum of the 2 classes bound, I can kind of assume that this seems like a really difficult problem. Now, it turns out it's not. I can actually give you a predictor that's automatically perfectly multi-calibrated, but with without seeing any samples. And the reason why is pretty straightforward. I already know exactly what one side of my domain looks like, just because I've told you it's the same for every single hypothesis. And on the right side, it really doesn't matter what I output because my class of subgroups doesn't care about that side. So even though it seemed like this class should be really hard to learn, we have a very trivial solution that took no samples. Are there any questions about this example and how I got here? So really the main takeaway of this example, and maybe even the broader takeaway from this talk that I think you should really come away with, I'll be happy if this is the only thing you remember, is that characterizing the sample complexity of realizable multi-calibration is going to require more than just kind of looking at these 2 classes independently. I'm not going to be able to find something where I look at one and look at the other and give you some combined value. I really need to understand how they're interacting, and then more how that interaction is going to affect what the sample complexity actually is. And so it turns out that the quantity we need is a somewhat natural extension of VC dimension. And this is something we call the mutual VC dimension. And so if you remember, I talked about how VC dimension cares about the maximum shattered sets of a class. Mutual VC dimension is going to look at all the sets shattered by my C and all the sets shattered by my H, and then look at the intersection. So look at all the sets that are shattered by both classes simultaneously. And I'm going to call the mutual VC dimension the size of the largest subset in that intersection. And so while we could kind of think of VC dimension as a notion of expressivity, you should maybe think of mutual VC dimension as a notion of shared expressivity. So how much the classes can express, but in the same place. And so to really drive home what I'm trying to define here, I'll just go over what it would be in this example we just saw. And so if we look at all the points shattered by C, that was 1/2 of the domain. All the points shattered by H was the other half of the domain. But the key is that these halves were disjoint. And so if I really care about looking at which points were simultaneously shattered, there weren't any. And so my VC dimension, or my mutual VC dimension, would be 0. And so this isn't like a proof that this is the right notion, but hopefully this is, maybe a vote of confidence that we're getting closer to the sort of quantity that we might like for this setting. So it does turn out that this is what we want. And so we're able to characterize the sample complexity of realizable multi-calibration by this mutual VC dimension. And this is when H and C are both binary hypothesis classes. And I said before, we can extend to real valued settings. And in this case, the notion that we use is we take VC dimension and we use the analogous notion that we often use in real valued, the fat shattering dimension. And we still kind of define it as this place where both sets are being shattered simultaneously. Are there any questions about any of that I went over? Cool. And so I think just one minor observation I want to make about this result is something that kind of comes from our definition of the mutual VC dimension, which is that it's somewhat symmetric. So I can take H and C or C and H, and I'm getting the same value, which kind of means I could flip my subgroup class and my hypothesis class in terms of multi-calibration and get around the same sample complexity. And this is a kind of property that we identified in a few of these related learning tasks. You can see more in our papers. We called it sample complexity duality, and it's very interesting to see where this appears and where it doesn't. And yeah, so I think quickly I'm going to look at a peek at how we get this result, because I don't want to just throw it on the board and tell you to believe me. And in order to do that, I want to go back to the multi-calibration algorithm that Michael very nicely presented on Monday. And I'm not going to go into as much detail, but the key takeaways from that algorithm was we start with some arbitrary predictor P, and we input this P along with some samples into some weak agnostic learner for C. And using this combination of inputs, we can get a good update direction for P, which can bring us closer to a multi-calibrated predictor. And then we can do this step again with the new P, and again and again and again until we get something that is a multi-calibrated predictor. As we saw, that we can bound the number of iterations. And so what we really care about in terms of sample complexity is how many samples do we need at each step in order to get this good update direction. The key insight for realizable multi-calibration is that this task is maybe a little bit stronger than what we need in this setting. We actually know something about the distribution we're seeing. So it's enough to actually use a weak agnostic learner for C with this assumption that our target distribution is part of a constrained class. And with that in mind, this is something that we study more broadly and call a comparative learning task. So kind of an agnostic learning task, but with another distributional assumption. And this is the task whose sample complexity we're able to bound by this mutual VC dimension. And through that argument, we can potentially reduce the number of samples you're using each step, and then reduce the overall sample complexity. Any questions about? Yes.
Even the px minus y.
Yeah, so you can think of this as we're looking for something with like a highly correlated, like a direction that's highly correlated with something we're doing bad on. So this is like my current predictor, whatever I'm inputting, and then this is like the true label. Does that make sense?
You're trying to learn on.
So could you repeat the point you mentioned that this is the weak agnostic learner is stronger than what you mean? Or?
Yeah, so basically, if I take away this, I'm saying, you know, I need a weak agnostic learner, and I'm not assuming anything about what the real ground truth distribution is. And here, I actually do know something about what my ground truth distribution is. I can assume that it looks like something from my class transformed by my current hypothesis. And that is like a strictly easier problem than just what I
don't need to boost over any distribution, just something that looks like this.
Exactly.
Okay.
Yeah. So with the time I have left, I want to go a little more deeply into this kind of agnostic learning task with a distributional assumption, just because I think it's interesting and worth looking at. And basically, as I kind of hinted and said more less formally in the last slide, what comparative learning really is doing is it's combining the realizable and agnostic learning tasks that most of you are likely familiar with. But just to go over again, in realizable learning, we make an assumption about our data. And so we assume that when we see labels, they're labeled according to some hypothesis that we can find in a constrained class. But then we still require the error of our hypothesis to be very, very low. And here, my error is just like the number of mistakes I'm making. I'm working in a binary setting. And then kind of alternatively, agnostic learning doesn't make any assumptions about my data. It says it could be anything, but I'm not going to require you to be like have really, really good error. I'm only going to require you to have error that's competitive with the best I could do from some constrained hypothesis class. And so the key thing to note here is that in both cases, I'm using a hypothesis class as a way to relax my assumptions, but it's being used in very different ways. And moreover, it's being used in ways that don't need to be mutually exclusive. And so comparative learning introduces two hypothesis classes. And it says that I have one that's kind of telling you something about what my data may look like. But then I also have a second that's I'm going to call a benchmark class that I'm using to compare what sort of error I'm getting. So, are there questions about this definition? And yeah, so this is the notion we end up calling comparative learning. And so in our paper, we show that this notion is what's characterized by the mutual VC dimension. And the proof is based on a reduction to another learning task of learning partial hypotheses, which I'm not going to get into here due to time, but the proof is actually quite simple. So I'm happy to talk about it offline to anyone who's interested. And more interestingly, we also explore comparative variance of other settings. So this notion of like having something with which we compare our error to, but also having a distributional assumption is not something that needs to stay in this binary hypothesis class case. We look at online learning, we look at boosting, so a notion of kind of boosting a weak comparative learner to a strong comparative learner, and then also regression, so where we might have real valued hypotheses and are trying to minimize some loss function. And I think the real takeaway here is that this notion of comparative learning really opens up this new setting with tons of different learning tasks that we could explore and try to understand better. But additionally, what's especially interesting is we saw that it maybe somewhat surprisingly had this application to multicalibration. And so it could be used as a tool for other problems. And so really exploring how else we might use this notion is, to me at least, a really interesting direction of future work. Yeah, and so that's all I have, but I want to put up these two papers here, especially because they look nothing like the title of the talk. And yeah, feel free to ask questions now or later. Yes.
So this symmetry in C and H, it seems at least as surprising in the comparative learning setting, right? Is there some intuition for why you should expect this to be symmetric?
So I guess in terms of how we develop the proof for this comparative learning case, we kind of take these two classes and merge them to look at a class that really captures where these two classes agree and where these two classes disagree. And so in terms of that, there's maybe a symmetry between, you can't really decide whether it's better for, like, if there's a disagreement, maybe it's equally weighted towards like whether you prefer the thing we're comparing against or the thing that you're getting your data from.
It's like, what is truth and what's the hypothesis?
Exactly. So that's maybe my high level. I think that it's an interesting question that would be interesting to explore. I think something else surprising is we get this duality in the distribution free setting where we're not making any assumptions about the distribution, but we can show that it breaks down when you're making some assumption about what your distribution over like X's may look like. And so it doesn't always hold.
Sorry, can you say more about that? You're saying that if your distribution on X is the uniform distribution or some known distribution.
I think our result is that there is a worst case fixed distribution over X where you can't flip them around.
So it seems that these results are kind of like statistical in nature. Like they say like how many samples do I need to learn this class? Mm-hmm. And then do they also say anything about the computational hardness of implementing learning over these classes? Like maybe learning over one class is hard and learning over the other class is hard. But once I come to the intersection, the search problem could maybe become easier.
Yeah, I think that's an interesting question. I'm not sure. I'd have to think more about that. I think certainly in terms of the example I gave, you pull out this very simple thing, but it also required like maybe a deeper understanding of what's going on in both of these classes that might be like kind of required in order to pull out this simpler example.
Any other questions? Yeah.